Thank you for the thank you for the introduction, and I'm very happy to be here to present this collaborative work with Niccolò Veltri. And then so just to begin of my talk, I would like to start from a quick recap about associative Lambek calculus, and in here it is just and here there are three connectives, just right implication, left implication, and also tensor. And here the sequence in associative Lambek calculus is antecedents, just a list of formulae. And then here are the derivations for this calculus, where just one axiom rule and also one right introduction rule and one left introduction rule for each connective. And then what about the cuts at the mean superior for associative Lambek calculus? It means that this rule here, cuts, is at the municipal, and the proof of the admissibility is by induction on height of derivations and also the complexity of cuts formulae. And in proving this, in some cases we have to check the relative positions of the cuts formula and the principal formula of a left introduction rule. So for example here, so we consider the right premise or the second premise is a conclusion of a implication left rule, and this cut here is applicable, which it actually tells us an equation of two lists. This gamma 0 A and gamma 1 is equal to lambda 0, lambda 1, A prime implies B prime, and lambda 2, right? Because this A can be coming here, so which means that A is somewhere in here, and then here there are four possibilities of the equation, where A is this principal formula, or A is in lambda 0, in lambda 1, or in lambda 2, which is pretty visible from the calculus. And then what about in the what about in the non-associative Lambek calculus and in here the sequence are of the form like this, where the antecedents here are binary trees instead of list. And so trees are defined by this grammar. So a formula is a tree, and if we have two trees, we can form a new tree. In order to define a substitution of trees, so we need to define a thing of context where there's a tree with trees with a hole. So in here, a hole is a context, and if we have a context, and then we can put a tree on, its right or on its left. Then with this definition, we can define the substitution for a tree U into a hole of a context C. And then here are the derivation, and here are the rules of derivations in NL, which are very similar to the rules in associative Lambek calculus, but of course the antecedents are different. And then cuts admissibility for NL. I mean, the proof here proceeds similarly to the case of associative Lambek calculus, and so we can see this example. And the second premise is also a conclusion of a implication left rule, and this cut is applicable. Tells us this equation of two substituted trees where CA is equal to C prime V and A prime implies B prime. So in order to prove cuts admissibility for NL, we also need to figure out all possibilities of the equation. And in general, we have to distinguish all possible cases of this equation of two complex C1, C2, and also two trees will be substituted into C1 and C2 respectively. And here there are in total, and there are three groups of the cases, and in total 7 cases. So the first group is when U1 equals to, when U1 is equal to U2, and then the complex they are also equal. And the second group is that when one tree contains another, which means that, okay, so maybe U1 can contain U2 or U2 contains U1. And there are 4 cases because U1 can contain U2 in its left or right subtree, and also vice versa when U2 contains U1, and or two trees are the strong, because these two substituted trees they are representing the symmetry T, and then it is possible that one is in the left subtree and one is in the right subtree, and then also the dual case. So the proof of cut admissibility for NL is kind of a doable on pen paper. You just need to be very careful. However, when we are trying to prove some more complicated properties, so for example, the associativity and the associativity and commutativity of cuts. So for example here, and the thing above is about the associativity of cuts. So meaning that, okay, if we have 3 derivatives, we can first cut f and g and then cut with h, and this derivation according to the according to the procedure we eliminate the cuts should be equal to, we first cut with g and h and then cut with f, or and here is the commutativity of cuts. So where we have a derivation h, and in which we have 2 places for the cuts, and we also have 2 derivations f and g, and the order of cutting g and f does not matter, and in the end they will produce the same derivation. And improving these properties, the number of cases just increases drastically, which is not easy to check on pen and paper. And therefore, we use the proof assistance Agda to help us do the proofs carefully. And here we're going to see the base of the formalization. And here we define trees in this inductive data type, where it's called tree. And here there are three constructors, and the first constructor is the bullet means that a whole is a tree, and the second constructor tells us that okay, so every formula is a tree, and we also have a comma just that we have two trees, and then we can construct a new tree. And as you can see in here, this type does not correspond to the tree we just defined on this paper. No, yeah, and I would say it is more like a mixture of it. It is more like a mixture of context and trees, and also in here we allow a tree can contain more than one whole. Okay, and then in order to define the substitution, accurately and also explicitly, we define the path. We define a type of path, and in here we overload the notation bullets, and here this means the empty path, which is the only possible path of a whole. And then this left and right triangle just to telling you where the whole is. So in here, if we have a path in a city and we are given another tree view, we can form a new path in this new tree view where this left triangle is telling you that the whole is in the left subtree, and then the right triangle is just telling you that the whole is in the right subtree. And then we can define the substitution as you might expect. And then here is one example about how we write trees and paths in the formalization. Okay, so this diagram is the tree where we have three leaves. The X and Y here is just atomic formulae. And then this tree is written like this, and here there is a hole in this tree where the path in the hole is written like this, which we should read as here. Okay, if we start from the root node and then we go left for one step, and then we go right for another step where we will reach the hole. And then we can formalize the case this distinction type. So in Agda, this equality of two substituted trees is written as this propositional equality. Okay, and then here the seven cases are just formalized here, and then this case one the same like U1 is equal to U2, and then case 2 to 5 just one contains another, and case 6 and case 7 just these those cases, and this genotype is correct because for any U1 U2 and for any U1, U2, and two paths P1, P2 in two contexts C1, C2, this type, so that we can construct functions from this type to this propositional equality, and we also can construct a function to this propositional equality to this type. So yes, and then we can continue about So now I will discuss two cases. And the first case is when U1 is equal to U2. And this case is pretty straightforward. And in here, this U1 equal to U2, and also C1 is equal to C2, and then also their path should be equal. And we collect this information in this record type, just three equalities we just mentioned. And then what about the second case where U1 contains U2 in its left subtree? And then in here is one example. In general, in this case, there exists trees W1 and W2, and the path Q in W1. And here you can think of like here, the W1 and W2 can be think of like a okay. So in here the W2 is the right subtree of U1, and then this W1 is the left subtree of U1, but we replace U2 with a hole. So in here, maybe we can see more clear presentation here. Given this particular example, in here, this U1, which is this part, is and its right subtree is W2, and also you can see that its left subtree is actually W1 when we substitute U2 for the whole along with the path Q. And then we can also see that here the red part is the path from the root node to the hole where U2 should be substituted in, and it is equal to P1 concatenated with vertical left and then continue with Q. So we collect the all information we just got into this record type where we have two trees, W1 and W2, and also a path in W1, and also three equalities just telling us about how the context can be equal, and also the equation between U1, U2, and P1, P2. Then we can use that data type to help us to prove Hart's admissibility for NL in Agda, and then so the Cutts rule in NL will be formalized as this function where it takes a path in a context C, so a path in here, and then two derivations, and then we can provide the conclusion here. As we expect it, and then the of the function Cutts proceeds by pattern matching on the second premise, and we can recall this example again, which tells us this equation of two substituted trees, and then we can use the sub-X type, where sub-X type will tell us four possibilities, and then maybe you wonder that, but I mean, in the original definitions, there are 7 cases, but here we are going to figure out we are going to figure out the relative positions of A and this string A prime equals B prime. So if we think of this A is U1, and then this whole thing is U2. So apparently it's not possible that U1 is equal to U2 or U1 contains U or U1 contains U2. So that there are only 4 possible cases are left. And the first case is when U2, so this thing, U2 contains U1 in its right subtree, which means this A is equal to A prime implies B prime, or it contains A in its left subtree, or they are disjoint. And then we need to provide a solution for each case. And we can do that. And in this paper, we are also hearing about the equational theory of derivations. And then in here we define the equivalence relation on derivations. And here are 3 classes of permutative conversions. And the first group is when the right row can be permuted with a left row. And the second group is when there is and the second group is sequential application of left rows, and the third group is a parallel application of left rows. Then because we consider the equational theory of derivations, therefore all admissible rules and constructions on derivations must be well defined with respect to the equivalence relation. And this means that the cut procedure must produce equivalence outputs when applied to equivalent inputs. So this statement is formalized as 2 functions, where the first one is called one is when you have two equivalent derivations f and f prime, and if you cut it with the same derivation g, and the resulting derivation should be equivalent. And cut 2 just when you have two derivations are equivalent, and then if you cut the same thing to them respectively, and then the resulting derivation should also be equivalent. And we can also, and then we can do more things with the help of Lambek. And the first thing is we prove the Metatheory integration. The saying that okay, so given a derivation f, and then we have a procedure to find a formula d, and also 2 derivations given h, and also this d will satisfy the variable condition. And moreover, because we have defined an interpolation procedure, and we are also caring about the equational theory of derivations, we also prove the well-definedness of the interpolation procedure, saying that given 2 derivations f and f prime, if f is equivalent to f prime, and then the interpolants triples found by the interpolation procedure respectively, their interpolants formula D and D prime will be equal, and also the derivation found G prime and H and X prime will be equivalent respectively. And then we also proved the proof relevance in the reason, just saying that, okay, if we have the derivation F, and then we apply the interpolation procedure on this, and then we'll find two derivations, G and H. And now, if we cut G and H back, which will return an equivalent derivation with 2F. Okay, so here are our results. And then to conclude my talk, so we have presented an Agda for formalization of NL. And we also showed that the proof of cuts at the reusability and also various properties related to cuts, and also Metatheory in interpolation. And also this formal characterization of the case distinction on the equality of substitutories, we think it should serve as the background for future formalization of other properties. And for the future, we would like to formalize the sumness and completeness with respect to the Hilbert calculus, not only on the probability level, but also on the proof level. And we also would like to strengthen the variable condition to include the multiplicity and also the polarity of occurrences of atomic formulae. And we also would like to generalize the well-definedness of the interpolation procedure with respect to the equivalence relation on derivation to some richer substructural logics. And the final thing is that if you are interested in the formalization course and you are welcome to visit this GitHub repository. And this is my talk, and thank you very much.